Hello and again, welcome to our channel. So today we are going to discuss about the partial differentiation. So I've made several videos on the partial differentiation, and the video that I made was not that much advanced level because it discussed about what is the total derivative, what is a differential, and the basic terms that how to solve the yeah, differential equations with the use of the exact and the inexact differentials. We have made a video on that you can watch. So in this particular video, we are going to discuss about that what exactly is the stationary values and how to do these stationary values in the partial differentiations when you have a function which depends upon two, which is x and y. Two coordinates, you can say x and y, not only on just one function. That's why it's a bit difficult to find out these stationary values. But yes, we are going to do this in video. And also we are going to find out the stationary values of any function when there is a certain type of the constraint. So let's start our today's video. So first of all, what is the meaning of these stationary videos we have to understand? After this, we will just start the all of the mathematical part of this. So the stationary values means what should be the stationary values contains of the maxima, minima, and the saddle point of the function. This means the stationary value means the maxima of the given function, the minima of the given function, and the saddle point, which indicates that it is neither maxima nor minima, and that is a saddle point. So in this video, that's the meaning of the stationary values generally to find out the value of x and y where the function is minimum, maximum, and has saddle point. And that is the basic meaning of the stationary values. So now let's dive into the mathematical part of this particular thing. So in one dimension, generally it is in one dimension means if you have a function which is only dependent upon x. So let's say a very easy case when there is a function which also only depends upon x. So what you do? What we do is that first of all, if there is a function given, we differentiate the function, equate with it 0, and the value of x, and after this, the value of x that we got, the value of x that we got, we just now again differentiate this particular f dash x, which is the double differentiation of this function. And if the double differentiation of this particular function is greater than 1 minute, so if this is greater than 0, then the value of x that we have got is the minima. And if first case, and the second case is if the f double x is greater than 0, while putting the value of x, it means हम लोग सबसे पहले f डबल डैश x को कैलकुलेट करेंगे, फिर x के वैल्यूज को पुट करेंगे, अगर अगर वो 0 से बड़ा है तो वो x का वैल्यू हमारा मिनिमा है. एंड सेकंड सिचुएशन इज दैट वी विल अगेन डू द डबल डिफरेंशिएशन एंड पुट द वैल्यू ऑफ x, एंड इफ द फंक्शन that we got is less than 0, then the value of x indicates that it is maxima. It's maxima. That is the general typical meaning of the maxima and the minima in the one dimension. And this is what we are going to study in the further to the when the function which is dependent upon two things, also on x and also on y. So let's start. This is the basic idea in the one dimension finding the stationary values. And third case is also there. So third case is f double dash x is equals to, sorry, if f double dash x is equals to 0, then it is a saddle point. It means the function is either not decreasing or increasing. It's not both. Now let's move to the part of the where we have a function which is f x y. So we have function now, okay? Now we are not going to use the general derivative, we are going to use the partial derivative. So we have function fxy. Now the first step is that you have to take the del f upon del y. First of all, del x is equals to 0. You have to put And the second thing is that just like you have to now differentiate this del f divided by del y is equals to the 0. First of all, you have to do this. You have to partial differentiate the function, equate with is 0 with respect to x first time, and second time you again do the partial differentiation of the f, but now with respect to the y and equate it with 0. Okay, quite simple. And after this, what you should do is that after this step, you got the value of x something and the value of y something. Okay, so you got the value of x and y something after doing this. Now what you have to do is that now you have to again do the double differentiation of this particular function, which is represented as f x x. So what this mean? I will explain it. First of all, let me write and f y y. Okay, so the meaning is fxx is nothing. This meaning is similar. I will write here. This is the notation. So fxx is a notation of the double differentiation of the function f with respect to the x. And just like this, f subscript yy means differentiation of f with respect to the y. And there is one more notation which is fxy. This is equals to the differentiation of f, and here it's del x and del y. 1 minute, del x and del y. And third is fyx is equals to del square f del y del x. See, these are four notations that we are going to use. So these notations are very useful. And these are the basis notations that you have to understand, because writing del square f and del x square, sorry, it should be square, is quite complex. That's why this is the small notations of this particular thing. Okay, now you obtained fxx, which means the double differentiation of f with respect to the x and double differentiation of f with respect to the y. Now, when you plug down the values and if fx x is greater than 0, then the value of x that you obtained is minima. Second condition, that if f(y) is greater than 0, again the value of y that you got is minima. This is the first criteria. Second is, if the value of fxx is less than 0, just like in the case of the only one function case, it represents the maxima. It represents the maxima, and just like this here, if fyy is less than 0, it represents the maxima. That value of y represent the maxima. And that is the meaning of the maxima and minima in the case where there is a function which depends upon x and y both. So that's the simple meaning of the maxima and minima in the partial differentiation. Now, we have discussed about this particular thing, that how to deal with this is very simple case, because only you have to do is that you have to first of all simply partial derivative of x and y separately, equate with 0, and you will get x and y, and then again do the double differentiation of the function, And the function that you obtained, you have to put the value of x that you got, and if this is if this is greater than 0 and if this is less than 0, you will get the maxima and minima respectively. And that's what's the meaning of doing the stationary values, finding the stationary values in the two-dimensional case. Two-dimension means x and y, function of x and y. So now we are going to study that how to deal when there is the constraint of the function. Constraint means you can understand as some sort of resistance to that motion. Like you studied in Lagrangian mechanics, that there is a constraint in this direction. It means you are not allowed to move in that particular direction, and that's the meaning of the constraint. Just like this, when you have some sort of functions, but the fact is that the values of function cannot go down the values of x and y in this x and y of this certainly particular values, then there is a constraint. Meaning is that here the x and y are independent of each other. But when you introduce the constraint, the x and y become dependent of each other. And because they are dependent of each other, because we introduce a constraint. Without constraint, they are free, they are independent. But when you introduce constraint, they are not free, they are not independent. Now they are dependent. So now if we have some sort of constraint, then how can we do the maxima and minima of the function? So let's see. But how the constraint affects. The fact is that if there is a constraint, and let's say constraint doesn't allow the value of x to be 0, so you cannot take the value of x to be as a maxima and minima. Why? Because the value of 0 is because it is not allowed to put down the value of this particular value of x, because there is a constraint in this particular equation, constraint in this particular function. So now let's start the constraint part. So now we are going to study the constraint part. Constraint motion. Okay. How to deal with this? Again, you have some sort of function. Let's have xy. 1 minute. And a constraint. And let's denote that particular constraint with gxy is equals to c. Where c is some sort of constant. Okay. So this is our general condition. If you know that how to represent the differential of a function, because I have made on this particular thing, that the differential of the function is equals to the del f divided by del x into this dx plus del f divided by del y into di. This is how we define the differential, which means the small change, infinitely small change in the function fxy we define with this particular formula. If you're not familiar with this, I've made a video on that. You can watch that particular video. So this is generally the differential of an element. Okay. So if you have a differential of an element like this, now you introduce another small change in differential dg, where dg is our constraint, which is equals to del z upon del x dx. Okay, but now we are going to introduce here some numbers, so let's see what exactly the number will be. And here it's del z g divided by del y into dy. Now there is another way to find out the maximum and the minimum, which is the stationary values of the function in the constraint. But the more easy way is to introduce a number called the Lagrange multiplier. So this is the Lagrange multiplier. You just you just add this particular number with this as this particular lambda, let's say lambda, into your equations, and you will automatically get your exact values of the stationary values of the maxima and minima. The more advanced use of this Lagrange multiplier will be in the Lagrangian mechanics. Okay, so it is Lagrange multiplier. Okay, let's say the short for Lagrange multiplier. So what we are going to do is that we are going to uh, multiply this particular equation with lambda. You have two equation, equation number one and equation number two. What you have to do? You have to add these two equation. It means next step is 1 plus 2. What will happen? df plus lambda dz is equals to taking dx common. 1 minute. Here it is equals to del f by del x plus lambda del, sorry, it's del z by del x, and it's dx plus del f by del y plus del g by del y lambda and here dy. So this is our particular equation after this. So after this, what we are going to do is that we are going to equate this particular quantity with equals to the 0, which means here I am going to do, then the second step is going to be that we are going to del f by del x plus lambda del g by del x, sorry, del z by del x is equals to 0. Let's say this is our equation number 4. Then also del f by del y plus lambda del f by del y equals to 0, just in the case like of this particular quantity is equals to 0. Let's say this is equation number 5. And our last equation gxy is equals to, let's say, c. Now let's say this is our equation number 6. Now you have three variables, which is lambda x and y. Now you only have to do is that you have to find out first of all value of lambda, then you can respectively find out the value of x and y. And the thing is that when you solve the equation, the value of x and y that you got is the value of x and y in the given constraint. And that's the beauty of the Lagrange multiplier, that it simplifies all of the calculation and it allows you to calculate the maximum and the minimum of a function in the given constraint very easily. You have three equation, you have three variables. This is three equation I think, and three variables are there. You can generally solve this and you will get the value of x, y, and the value of the maxima and the minima and the given constraint. If there is no constraint, then this all summarizes to our upper part that we have studied. But here there is constraint. Okay, if there is no constraint, you can generally do all of the stuffs that we have done here. But if there is a constraint, you have to do this. And after equating with 0, you will get what you have to find out the x and y. But again, you cannot understand it by the way the example. So in constraint part, I'm going to take an example. So let's see. Here there's a question. Sure. The question is the temperature x and y is equals to the 1 plus xy, but the fact is that, but the constraint is that it only moves, it only can be found out in the x square plus y square equation, which is equals to 1, which is the circle equation. If I study the coordinate geometry, this is a circle equation. So you have your temperature, you have your constraint x square plus y square is equals to 1. What you all have to do is that just follow all these steps that I have done. First of all, you have to differentiate f with respect to the x. F, our function here is temperature, which means we are going to do del T by del x. Okay, then plus lambda del G by del x and equate it with 0. Then let's calculate this. So del T by del x will be nothing, it will be x. Sorry, y. It will be y plus lambda into del G divided by del x, which will be your, I guess, 2x is equals to 0. In a more better form, y plus 2 lambda x is equals to 0. Let's say this is our equation number 1. Just like this, what you have to do is that you have to calculate now del T by del y plus lambda into del G by del y equate with it 0. Now you have to differentiate t with respect to the y, which will get you x plus lambda into 2y is equals to the 0. Sorry, it's 0. Now arranging this, it will be x plus 2 lambda y is equals to the 0. This is our equation number 2. And the third equation is your gxy equation, which is equals to the x square plus y square is equals to 1. 1 minute. It is equals to 1. Let's say this is our equation number 3. Now you have three equation, okay? Three variable, y, x, and lambda. Just solve this and you will get the value of x, y respectively. But you have to find out that what value of x and what value of y are maxima and minima, and that is quite easy. Just follow the step that we have done in the without constraint section. Just differentiate the function again with respect to the x, and if it's equal to, sorry, if it's more than 0 or less than 0, it will be minima and the maxima respectively. So let me show you that how to solve this. It's very easy. So we have three equations, or what we can do is that, okay, so from the first equation, we can substitute y is equals to negative 2 lambda x. Okay. So putting this value of y in our equation number, let's see, equation number 2. Okay. What will happen? 1 minute. Okay. Putting the value of y is equals to 2 lambda x. Let's see what will happen here. X. Okay. Now putting the value, what you will get is x plus 2 lambda. Here it is negative 2 lambda x. It's 2 lambda x is equals to the 0. Now x minus 2 lambda square x is equals to 0. And now it's very easy to solve. X is equals to 2 lambda square x. X and x will cut out. lambda is equals to plus minus 1 over root 2. I found the value of lambda. What you have to do is that now substitute these values in the given equation and find out the value of x and y respectively. First of all, put the value of lambda as plus 1 by 2 and then minus 1 by 2 and get the values of two values of x and y, and one you will get for the saddle point of x and y. And that's the easy way. By introducing the Lagrange multiplier, we can generally solve this particular problem, because using the other methods, it will look like hell. That's why the Lagrange multiplier method is very necessary. And this is also necessary in the Lagrangian mechanics. That's why when I will start the advanced series of the Lagrangian mechanics, it will be very helpful to use the Lagrange multiplier, because it's the core of the Hamiltonian principle. When we deal with constraints in the classical mechanics, using a Hamiltonian principle with the Lagrange multiplier is awesome. Okay, so it will be very good. So this is my today's video on the stationary values with the constraint or without the constraint. Hope that you understand all that things, and if you have doubt, you can comment your doubts in the comment section. I will try to solve it out. So thank you for today's video.